mathematically, we would write that as the surface integral over the surface S of B dot ds. So flux is just the amount of magnetic flux density going through that surface. And it has the symbol capital phi, which looks like this, like an eye with a circle around it. So that's magnetic flux. But we're talking about inductors and inductance, and for that we need another quantity called flux linkage. What if we took the same surface and the same magnetic field? So the magnetic flux through that surface is still the same, but then we had a current that was flowing around that field, and the wire was wrapped around the edge of the surface multiple times. There were a lot of loops of current going around the same surface. In that case, the flux linkage is the number of times that flux goes through a loop of the same current. I guess not the number of times, because it's actually an amount of flux. So the amount of flux that goes through a loop of the same current. So that means that double counting is okay. And in fact, it is what you want. The flux linkage is the number of loops times the flux that those loops are going around. And that has a different symbol. It's this, which is a capital lambda. So if there's n loops, it's going to be n times the magnetic flux is the flux linkage. Now we know enough to talk about inductance. Which is defined, we give it the variable L, and it is defined as the amount of flux linkage per unit current. And it has units of henries, whose symbol is a capital H. Now, this is self-inductance. If when the flux that's giving us the flux linkage is due to the current that we're referring to, right? So when that flux linkage comes from that same current I. You can also have a mutual inductance. and it also has to go through loops that I is making. You can also have a mutual inductance, though. That's when some current I1 generates the field for the flux linkage, but the field is going through loops of a second current. That happens sometimes when you put two loops right next to each other. That is also the way that NFC, near field charging, works. So if you have one of those phones that you can just set down on a special pad and it charges itself and you don't need to plug it in, it's working this way using mutual inductance. Okay, last topic, and then we're going to do an example. The last topic here is magnetic energy. When we're talking about Faraday's law, I will tell you why the voltage across an inductor is equal to L di dt. For right now, we don't have enough information to derive why that is. So I just want to tell you that, and hopefully you remember this from circuits 2 or maybe even circuits 1. And we're going to use that fact to find how much energy is stored in the magnetic field of an inductor. So the power is always in the time domain. So this is voltage of time, current as a function of time, power also as a function of time now. And in the time domain, voltage times current gives you power. And the total amount of energy that you deliver to something is just going to be the integral of power with respect to time, which means that that would be the same as writing IV dt, right? I could write it that way, which using this expression up here, which relates the voltage and the current in an inductor to each other, that means that the energy that I've stored in an inductor is equal to the integral of I times the voltage, which is now L di dt, dt. Now the inductance isn't changing with time unless we're in a very special situation, so we're not going to worry about that. So we can move the inductance out to the front, and then we have I di, because this dt and this dt and this dt are going to cancel each other effectively. Evaluating this integral, we just get 1/2 I squared, because that's a pretty straightforward integral. So then the energy stored in an inductor, and we usually use Wm for that, for the magnetic stored energy, is just 1/2 L I squared.